Howdy! At this point, we have a basic understanding of the derivative, and we can calculate derivatives using the limit definition of the derivative. But that ends up being quite painful at times. We not only have to evaluate a limit, but usually we have a lot of algebraic manipulation that we have to do, and it takes a lot of time. What we want to spend the next several classes doing is we want to develop a bunch of tools that we can use to differentiate different types of functions without having to go through all of the gymnastics of evaluating all of these different limits. Now, what we're going to look at right now are power functions, meaning functions that are in the form x to a power, x squared, x cubed, x to the fourth, but also x to the negative third, x to the 1/2, etc., etc. And there's a rule that we're going to develop that's going to help us a lot called the power rule. So what I want to do is I want to look at some derivatives of power functions, and we're going to look for a pattern that's going to show us what we get. So let's consider first f of x equals x to the first power. Now, this is a linear function. Its graph is a line with slope 1, so we would expect the derivative to be 1, because the derivative is the slope of the tangent line, but let's use the limit definition just to see if this is true. We've got f prime of x equals the limit as h approaches 0 of... We've got f of x plus h, which is just going to be x plus h, because f of x is just x, so f of x plus h is x plus h, minus f of x, which in this case is just x, all over h. Now, in the numerator, we can see that those x's are going to cancel out, and all we're left with is h over h, which is 1. So we've got the limit as h approaches 0 of 1, but that is just 1. So we know that the derivative of x to the first power is just x. All right, I want to talk about some higher powers of x, but there's a few we've already seen. If we look at f of x equals x squared, we have already differentiated this as an example. We saw that f prime of x, in this case, is 2x. Similarly, we've also differentiated x cubed. We saw that the derivative of x cubed was 3x squared. What I want to do next is I want to look at the derivative of x to the fourth. I want one more example so we can start to see a pattern. To differentiate this, we need to use the limit definition again. F prime of x equals the limit as h approaches 0 of f of x plus h, that's going to be x plus h to the fourth power, minus f of x, which is x to the fourth, all over h. Now, we have to expand x plus h to the fourth power, and I am not going to do that in this video. I don't want to make this video really long. Also, at this point, you should have the algebraic capacity to do that on your own. So I'm going to leave that as an exercise for you to do on your own. And I'm just going to give you what we get when we do that expansion. We have the limit as h approaches 0 of... And when we expand x plus h to the fourth, we're going to end up with x to the fourth plus 4 times x cubed times h plus 6 x squared h squared plus 4 xh cubed plus h to the fourth. And then we still have that minus x to the fourth, and this is all over h. Now, we can cancel out the x to the fourths because we've got a positive x to the fourth and a negative x to the fourth. And then we can divide all of those remaining terms by h. So 4x cubed h divided by h is 4x cubed. And then plus 6x squared h squared divided by h is 6x squared h. And as we continue, we're going to get 4xh squared. And then h cubed. H to the fourth divided by h is h cubed. And we're looking at the limit as h approaches 0. All of those terms except for one have an h in them, so all of those terms are going to vanish when we plug in 0 for h, and we are left with just 4x cubed. So what I want to do is I want to look at all of the derivatives that we have so far, and I want to look for a pattern. So we're going to make a little table here. We've got our function, and we want to look at the corresponding derivative. All right, our functions, we had x to the first, x to the second, x to the third, and x to the fourth. And our derivatives then were 1, and then 2x, and then 3x squared, and then 4x cubed. And I want you to take a moment and see if you can figure out what the pattern is, because there is a pattern here. All right, if we look at x to the fourth, well, each one of these has a coefficient out front, and you can see the coefficients are 1, 2, 3, and 4. Where do these come from? Well, these come from the exponent. The number out front, that coefficient, always comes from the exponent. We can see that those match. And then we're left with a power of x, and each of these powers of x are one smaller than what we started with. And so we can actually turn this into a rule. We call it the power rule, and it says if n is a positive integer, because we've only looked at positive integer exponents here, the derivative of x to the n power is n, so that power becomes the coefficient, just like we said, times x to the n minus 1. So if we want to differentiate something like x to the fifth, we can. We take that exponent, in this case n is 5, we put it out front, 5 times x to the fourth, because the power decreases by 1. If we wanted to differentiate x to the 10th, what would we get? Well, the exponent 10 goes out front as the coefficient, and we end up with the power decreasing by 1, so that's going to be 10x to the 9th power. That is the power rule, and there's some example problems in the videos for this lesson, so you can look at some more examples. But I want to do one more thing. I want to talk about other powers, powers that aren't integers, because we have powers that aren't positive integers, because we've seen some of these before. We've seen some examples. For example, if f of x equals 1 over x, we saw that the derivative was negative 1 over x squared. Now, we can also consider 1 over x to be x to the negative first. So if the function is x to the negative first, then the derivative is negative 1 x to the negative second. And again, you can see that the exponent, negative 1, becomes the coefficient. And then the original exponent, we subtract 1 to get the exponent of the derivative. Negative 1 minus 1 is negative 2. So this is an example that seems to show that this works even if n is a negative integer. If you want to see more examples, you can work some of those out on your own, and you will see that it is true. But they don't even have to be integers. We also saw that the derivative, and I'm going to use different notation just so we get practice with it, the derivative of the square root of x is equal to 1 over 2 root x. This was another example that we had done. And we can write the square root of x as x to the 1/2 power. And when we differentiate, this is 1/2 times x to the negative 1/2. Negative because we've got our x in the denominator, and 1/2 because the square root of x is x to the 1/2. So again, if we try to see if the power rule fits here, we take the exponent and pull it out front, 1/2 times x to the, and remember we decrease the power by 1. 1/2 minus 1 is negative 1/2. So it seems to work here. And I'm just going to tell you that, in fact, it works for any real number as an exponent. Bing! The general power rule says if n is any real number, then the derivative of x to the n power is equal to n times x to the n minus first. So we can pick any power of x and differentiate using this rule. You'll see some example problems that do ones where the exponent isn't a positive integer as well.